Just a word or two on the Chicago Council on Science and Technology. We are an organization composed of all of the major science and technology generating organizations in Chicago, universities, national laboratories, museums. Some of the industries, Exelon, Baxter, Labs, and our operation is geared to raising the awareness of science and critical issues in science and technology in the Chicagoland area. I'd like to phrase it by saying that would you rather get your information on critical science and technology issues from actors and actresses or from people who know something about the subject? So we're here to listen to people who know something about the subject. We've been in operation a little over 2 years, and I encourage those of you who are interested in the topic to join the organization. We have the sign-up sheets outside, and as I say, I encourage you to join. We've also passed out some cards so that you can fill them out and tell us what you think about the meeting this evening so that we can adjust ourselves accordingly. Well, my function is to tell you something about the organization, which I have done, and then to introduce the person who's going to introduce the speakers. And that person is Jay Walsh. Jay is the Vice President for Research at Northwestern University. Northwestern is one of the founding partners of C2ST and also provides a suite of offices for the organization. Jay received a bachelor's and master's degree in electrical engineering from MIT and a PhD in medical engineering from Harvard Medical School and also from the Massachusetts Institute of Technology. Joined Northwestern in 1988, and Jay, that's all the introduction you're going to get from me.
Well, thank you for the introduction and for the briefness of it. It's good. I actually get to introduce the moderator, who will introduce the speakers. So we have this daisy chain here. So the moderator today is Ruth Norton, and you can see from her bio that she's the chief conservator of the Field Museum now, and that she got a master's of science in art conservation at University of Delaware. What's not on the bio is that after being in Delaware, she went to Honolulu, and then the Philippines, then to Australia, then to Pella, Jordan, Middle East, and then back to Australia, then to Buffalo, New York, and then to Leiden, Netherlands. These are all the places she worked. She didn't just go visiting. She worked at all these places. She landed here in Chicago, but continues to work a little bit as an adjunct faculty in Buffalo. And not to keep things too local, she also spent some time in Malaysia and Cambodia, all doing art conservation work. We are absolutely delighted that she's here, as Al put it, to guide us and be one of the experts in this field and to introduce our speakers.
Thanks. I can't tell you how many trees I've planted to offset my carbon footprint while traveling around. Thanks for inviting me to be able to share this evening of what looks like the most interesting case studies here. The speakers are from the academic side of things, and on behalf of the museum side, I want to offer my heartfelt thanks to you all for the collaborations that have made our work possible, because it's the working together with the collections and with the scientific community that's really made preservation and conservation possible. And we've got plenty more material for you guys to work on. Say, for example, in the Field Museum Department of Anthropology, there are about 1.5 million objects. And even given that maybe a quarter of them might be stone small lithics, that's still a lot of material for problem solving out there, with looking at deterioration issues, looking at aging, materials composition. And we're very lucky this evening to hear 3 examples of collaboration, of looking into some very specific case studies of the kind of world that we all live in. This evening, the 3 speakers will each have about 10 to 15 minutes to describe what they're doing. And then to ask you to hold off on questions until the end of the presentations, since that many of the questions may be interrelated amongst the speakers, and it might be easier if we did them all together. So I'd like to hold off until the end, and then we'll have about 15 to 20 minutes for questions and discussions as you go. I'd like to first introduce Dr. Katherine Faber, who currently holds the position of the Howard P. Murphy Professor of Material Science and Engineering in the McCormick School of Engineering and Applied Science at Northwestern University. Her research interests include fracture of brittle materials, thermal shock, fatigue, and reliability. She is an ISI highly cited author in materials, recently completed a term as president of the American Ceramic Society, and served as a coordinator of the Art Institute of Chicago, Northwestern University Collaboration Program on Conservation Science. Dr. Faber.
The work I'm going to be describing this evening was done by both a student at Northwestern, but also in collaboration with folks at the Art Institute of Chicago, as you see, and also a high school teacher who spent some time with us one summer. And just to continue to follow the pattern here, I'm also going to make an introduction, and that is of this beautiful kneeling figure that is about 3,000 years old. It is a part of the Sewn and Shine collection of Asian jade, ancient jade objects at the Art Institute. The collection was bequeathed to the Art Institute in about 1950 and comprises about 850 pieces, so it's a huge collection. Later this evening we're going to hear about Le Grand Jatte, but according to the former curator of Asian art at the Art Institute, Jay Zhu, this was his Le Grand Jatte. And so we'll talk about the aspects of this figure that were so interesting to him. So before I get into a description of those studies, I would like to talk a little bit about this collaboration that we have between Northwestern and the Art Institute. About 8 years ago, the Mellon Foundation endowed the position of conservation scientist at the Art Institute. This was to be their first PhD level conservation scientist. And so some staff members from the Art Institute came to visit us at Northwestern and were concerned at the time that the individual that they would hire would not have a large community to work within, a community of scholars, and said to me at the time, would you have any interest? And we jumped at the chance to get involved in these types of problems. So 2 years later, Dr. Francesca Casadillo was hired as the Mellon conservation scientist, and within a year we went back to the Mellon Foundation and asked for some support. They gave us a little support to see if we really could work together, and once we proved that we could, they then awarded us with a 3-year grant to get this collaboration going. In December of this year, this support was renewed. And one of the things that we had to deal with at the university was to begin to educate people to the notion of conservation science. What is it? And so we have this nice array of definitions here of the particular discipline. And that ranges anywhere from treatments for damaged work, just the study of long-term aging for materials that might last over centuries, technical analysis of artist materials, analytical studies themselves of artifacts, and probably the one that you're most familiar with is determination of authenticity or forensics. So what does Northwestern bring to that partnership, knowing what conservation science is? Well, we see this as a way to talk about new areas of the application of technology. Our research facilities are available for these studies. New materials for conserving objects of cultural heritage. We feel we have a talented group of people, and ultimately would like to take that information to the broader community. So in terms of this collaboration, what we have offered both to Mellon in terms of their support of this is that we have put together basically a model for collaboration among museums and universities and scientific institutions that in the Chicago area has also included Argonne. And we hope that we can also enhance the field of conservation science in the nation and strengthen the Art Institute's research capabilities. So now with that as background, I would like to go back, one more thing that you might be interested in. Part of this collaboration includes a seminar series, and through the years we have had seminars that focus on things like color science, like 3D imaging, as well as specific materials such as metallic artifacts, ceramics and glasses, and house paints as they introduced into the artist palettes, say with Picasso. So if you'd like more information on these and would like to get on our mailing list for these, please make sure you talk to me afterwards. So now back to our kneeling figure. So one of the things that is curious about this piece is that it is very dark in color. Certainly not the color that one thinks of in terms of jade. In fact, when we think of jade, we think of materials that have a much greener tone, maybe all the way to white. But when you think of jade in the context of ancient China, jade really referred to any beautiful stone. The important thing was that that stone had to be soft enough to carve into intricate shapes, as I've shown here. But chemically, jade could refer to what we now think of as traditional jade materials, such as nephrite or jadeite. But it could also include materials that were not quite as jade-like as these, things like the chlorite minerals. And these all contain elements such as silicon, aluminum, sodium or calcium, magnesium, iron, and of course oxygen. They're all oxides. And so with that in mind, we could then, knowing this broad definition of jade, we could then go back and look at this the kneeling figure and say, okay, with that in mind, what are the possibilities that might make this statue so dark in color? And so in our analysis, we said, okay, we could come up with about 4 possibilities. One could be that the figure was treated with some sort of a paint or coating. In addition, it could have been heated as part of a ritual or as part of a workshop practice to perhaps make it more carvable. Had the piece been polished or impregnated with some high wax, some wax-like substance in the course of trying to sell the piece to a collector. So these were our possibilities, and with that in mind, we then brought our kneeling figure up the lake from the Art Institute to Northwestern, which is quite an ordeal in itself. And from that began to look at each of these possibilities. So the first was to examine whether or not the piece was painted. And to do that, you now see a different view of the kneeling figure. He's no longer kneeling, he's on his back. And he is placed into a scanning electron microscope. And with that technique, we are able to basically look at topography of the surface. Okay, so we're looking at surface roughness areas, particularly around scratches. So remember, this is now 3,000 years old. He's been through a lot. He's patched in a few places, so he's needed some repair work. But what was most important is when we looked at areas around scratches, if the object had been painted, you would have been able to see an area of delamination there. And there was no evidence of that anywhere in the piece. So with that in mind, we then went on to option 2 and said, okay, could it have gone through some ritual? And in order to replicate an experiment like that, we had to determine what we had there. What was the mineral that we were working with? So our kneeling figure was then X-rayed. And so we used a technique known as X-ray diffraction here, where one reflects X-rays in the surface layer of the material. And what we're measuring here is actually the spacing between atomic planes. And for a given chemistry and given structure, this is basically a fingerprint of the material. So for a given angle of incidence here, when the X-ray waves are in phase, we see high intensity peaks. And that allows us then, as the fingerprint, to determine what kind of a mineral our kneeling figure is. And so with that, we found that, that he is a clinochlore, or a chlorite structure. And from that, we could then find other chloride minerals that we could use and test in the laboratory, because of course, given the value of this object, we would not want to do any destructive testing. So what we did was to take pieces of chlorite and put them through a series of heating experiments, and from that watch to see if there's any change in color. And in fact, here is the dark gray unheat-treated material. And as this was exposed to higher and higher temperatures, and 600 C is certainly a legitimate temperature for a wood-burning fire, you see that the mineral gets much darker, and then if you go higher, it turns almost orange or reddish. And so that was an indication that there could be heat-induced color changes that may have occurred. We also found that in that experiment, the full interior of the chloride mineral was not changing color. It was only happening at the edge. And so this is an optical image showing the color change only occurs about 200 microns into the solid. And so that tells us that the process by which there's a color change, it's time dependent and temperature dependent, and we're looking then for this chemical change to move in from the surface. So with that in mind, we did yet another spectroscopic technique that told us that what was happening was that hydroxyl or OH groups that are in the chloride structure are actually diffusing out from the surface, and you can tell that this large red peak here is now being diminished as we go up higher and higher in temperature. So we're getting a chemical change by the evaporation of these OH groups, and the mineral is changing forms from chlorite to a phosphorite and ultimately to a spinel type structure. And we see this change in color having to do with the change in the oxidation state of iron. So the rust color that you see is due to iron 3+, just as you would see in rust in your car or in other things that in your home. So one last, just because we thought that heating was the reason for the color change, did not mean we could forget about those other two options. And so the last experiment here was to look at wax on the surface. It's well known that some art dealers use something known as Japan wax to sort of shine up objects to make them more attractive to a buyer. And so with a cotton swab, some of the sample was taken from the surface of our chloride samples, and this is, from the kneeling figure, this is what you see from the surface, and here's a spectrum then of Japan wax, and we see that they match quite well. And you can also see that in these pieces up here, in our chloride samples, that in fact the wax and the polishing and waxing gives the pieces a very dark color. So what are we left with? So in conclusion here, we were able to eliminate only one of the possibilities. But along the way, we learned about the mineral composition of the kneeling figure. We learned that the figure could have been heat treated, but in addition to that, that he has been polished along the way. So the answers are not definitive, but I think our Asian art curator was pleased that that the piece hadn't been painted. So with that, I will end here, and Ruth, am I handing it back to you or on to Ken?
I think so.
Okay.
Our next panelist is Dr. David Dunand, who is the James and Margie Krebs Professor of Materials Science and Engineering at Northwestern University. He teaches and does research in the area of lightweight metallic alloys, composites, and foams, with uses spanning from energy-efficient transportation and power generation to biomedical implants. He's published over 175 journal articles, and holds 8 patents. As co-director of the Initiative for Sustainability and Energy at Northwestern University, he is also involved with expanding research, teaching, and outreach on these topics at the university. David will speak on 20th century bronze analysis.
It's a pleasure to tell you a bit about this very exciting project that has to do with metallic composition of bronze objects that come from the Art Institute, as well as the Philadelphia Museum of Art. So this work was done by Marcus Young, who was a postdoc in my group, co-advised by Professor Lambert and myself at Northwestern University, with collaboration from people from the Art Institute of Chicago, and was part of that larger project that Professor Faber described a few minutes ago with financial support from the Mellon Foundation. So the goals for this project was to establish baseline information on the composition of those bronze objects, to give an idea for composition as they relate to repairs, for instance. Many of those objects need to be, in some cases, repaired, and also to establish whether the corrosion resistance of those bronzes was sufficient for long-term conservation. The other thing was the art history aspect, and what we wanted to do was to correlate the composition of those bronzes with the artist. We really had the pleasure of working with about 70 objects from different artists. And you can imagine, for instance, that the color of some of those objects might have been important for the artist. And he or she, mostly he in these cases, really might have said, I'd like to have this or that composition to achieve, for instance, a beautiful color, as the case for this Rinkuzi Dunand from 1913. But in most cases, those objects were actually patinated. So they have this very dark color, not unlike actually the type of dark color that Professor Faber described on her object, which is much older than ours. I should say that those, of course, are early first half of the 20th century. And the patination, this thick layer, of course, might eventually flake off over a long time, and this is back to conservation. We need to know about the composition of those bronze to address this potential issue. So what we want is also to create the composition with a family. I mean, the artist uses an object, but then this object needs to be cast in multiple castings, and there are different casting methods. The composition may have an impact on the castability, the ease with which they can cast those objects. So if they are very intricate, there might be a different composition for the metal than if it is a much less detailed object. And the artist may actually have a relationship with a particular foundry and may want to stay with that particular foundry. So we believe that we can make, we tried at least at the beginning with the idea that there might be a correlation between the composition that we can measure in the lab and some of those informations that may or may not be available. In many cases, for instance, the information about the foundry is lost. We don't know where the object was cast. And finally, the date is also very important. This is a single object, but it can be cast over a long period of time. There might be early castings and then a second series of castings, and so the data is important. And we thought that maybe the composition has changed with time, and that may be a way to extract some information on the date at which those objects were cast. So we have over 60 modern bronzes from the 1900 all the way to 1953. I've shown some examples here. This is Henri Matisse, Picasso, and Coupelet. Those were actually three artists from whom we had the largest number of objects. In fact, Picasso, we had 11 such objects. And we have a large number of rather well-known artists coming from the Art Institute of Chicago, as well as the Philadelphia Museum of Art. So the method that we used is something called inductively coupled plasma optical emission spectrometry. A bit of a mouthful, but it's actually very simple. We start actually drilling a small sample from those objects. This is again Rinkuzi's Dunand, and we go at the base and we do something that is actually quite amazing, and that is we drill into the object. Something that, of course, the museum doesn't want to do very often, and they ask us, of course, to take a very small amount. So this is disruptive testing. The good news is that the disruptive testing that we do is barely visible. We're talking about a few tens of milligrams, on the order of 10 milligrams. So those turnings are dissolved in a very strong acid, and that solution is then sprayed into an organic plasma, essentially a flame. And the different atoms, copper mostly, but other atoms, as we'll see in a moment, start emitting different colors. In fact, you can do this at home. If you take a candle and drop a grain of salt, you'll see a beautiful orange color. And that color is the fingerprint for sodium and chlorine that make up the salt. So each of the elements, and there are, we'll see, upwards of 15 elements in those castings, emits a different set of colors. Those can be measured. So you measure the actual color, we call this the wavelength, and we also measure the intensity. The wavelength will tell us which element is there, and the intensity will tell us how much of that element is there. And out of this, with some calibration, we can end up with a composition, as shown here, an elemental composition, unlike what Professor Faber showed you, which was really a composition of a particular compound. What we get is only the elements rather than a compound. So what we found out, in summary, is that, of course, not surprisingly, the base metal is copper. We have actually high copper level, 94%, as low as 2/3, 67%. Then there are three, what we call alloy elements that are being added on purpose by the foundry, and those are zinc and tin, which vary quite widely. So zinc is as low as 1 and as high as 33 weight percent, and tin varies over a narrow range between half and 6 weight percent. And then typically a bit of lead. The lead is added for the castability. It's easier to cast metal when there's a bit of lead in it. And then a whole bunch of trace elements here. Those are typically elements that are not added on purpose, but rather end up in the alloy because the starting metal may not have been very pure. In fact, in many cases, metals are recycled, and you end up with all kinds of elements starting with silver all the way to tungsten. So to give you an example, a Mayer woman with arm over eyes, 1900, consists of course mostly of copper, has about 6% zinc and about 2% tin with a 30% of lead, and the main trace element is iron. So we end up with this very large database of information. And what we decided to do is to try to correlate the amount of zinc with the amount of tin. Remember, there's always copper. But one of the questions we can ask is there more zinc or more tin? Because depending on the answer, you end up with a very different type of alloy. So what we can do now is plot the amount of zinc versus the amount of tin, which is shown here. This is one plot that will show over and over. And on the y-axis, again, zinc that goes from 0 to all the way to a very high level of about 33% zinc. And on the x-axis, we see the amount of tin, Sn, that varies less widely between 0 and a study over 6%. And all this large cloud of data point corresponds to the different artists as shown on the upper right. So how can we make sense of this? Well, the first thing we have to realize is that at the bottom right of the graph here, we have objects who contain more tin than zinc. Whereas up here, of course, we have objects that contain a lot more zinc than tin. In fact, the straight line here corresponds to the demarcation line between alloys that are richer in zinc and those at the bottom that are richer in tin. And those, as a metallurgist, are called respectively brasses and bronze. Now, in a museum environment, an art environment, we never say this is a brass. We say it's a bronze. Even though, as you can see, it's actually, many of those are brasses. So that's the first demarcation we can make. So the majority actually are brass objects. Now, the other thing is as we increase the amount of alloying elements, the melting point of the alloy is changing. We start with pure copper, which is at the origin here, melting point of about 1066 degrees centigrade. And as we alloy, that means as we go from the bottom left to the upper right here, the melting point of this alloy drops. That's very good if you're trying to cast metal. And so there might be a correlation here with the foundries and the way or the intricacy of the object. Because as the melting point drops from 1050, this is the series of points where the alloy exactly has 1050 C melting point, or 1000 C, or even 950 degrees C. As it cools down, as the temperature decreases, it's easier and easier to cast the alloy. So that's the second thing that we can put on this diagram. And once we do this, we can kind of squint our eyes and say, okay, there seems to be about 3 groups of objects. First, there is the bronzes. Put in here a circle with name C here. And then 2 types of brass alloys. One that is higher tin and higher zinc, and therefore melts at a lower temperature. And one that is less alloyed in both zinc and tin, and therefore melts at a higher temperature. So we end up with 3 clusters, as we call them, A, B, and C, with a few outliers. And the question now is whether we can find correlations between, for instance, artists and clusters. Let's look at Picasso, for instance. Picasso is the little star here. You see that almost all the Picassos are clustered in cluster A. So there's now a clear correlation between composition and artists in that particular case, which might be in fact useful if you have an object that whose provenance is unclear. People may actually say, well, is it or is it not a Picasso? Well, one piece of information that we can now produce is if the composition happens to fall in that same cluster, this is certainly an indication that it might be Picasso. Matisse is shown here, belongs to cluster B, and Hooplet, for instance, is visible in all three clusters. In that case, composition would not be very helpful. In fact, Hooplet is all the way up here as well in this outlier, which is almost pure, contains almost no tin and large amount of zinc. So this may work for some artists, but not others. So that was the first thing. Here is in fact this outlier cat, which just looking at it doesn't look any different from all the others, but is widely different in terms of composition as compared to all the other outliers. The next thing we did is correlate those data points with the foundry. Now, in many cases, but by far not all cases, there is a foundry mark on the piece, and so we were able to look at those different foundries, but in many other cases, there's no foundry mark. It would be actually very interesting to know where the object has been cast. And what you see is that the main, and I should say all those foundries are in the Parisian region. So all those objects were cast, without exception, near Paris. And the most important foundry at the time was Balstrani. And you see clearly that Balstrani is associated with cluster A, the low melting alloys that as we'll see in a moment, in fact, easier to cast. In fact, even those outliers here, see, make sense. They melt at roughly the same melting point than the other ones. This is an example of Picasso, and here's an example of this cluster C. This is Roudier from Daubigny-Ratapoil. You see that all the Roudier are actually in the bronze region here. So for those two cases, Balstrani and Roudier, we see a clear demarcation, maybe with one exception here, for foundries. So some very useful information if we don't know. For instance, here's a bunch of points for which we have no information about the foundry. Well, it might be Roudier, Balstrani, sorry, or even Evrard, which is the black dot here. The third thing we did is we tried to correlate those different clusters with the date at which it was cast. This is not the date at which the object is created by the artist, but rather the casting date. And in color we see in black we have essentially pre-World War I. In red we have post-World War II, and you see a clear demarcation between red points and black points. So as objects get old, I mean, for the first, the older object, for instance, Matisse, the Serre, in the early 1900s, they tend to be low alloy objects, which melt at high temperature. And for objects that were cast later, for instance, this Picasso Standing Woman, those tend to be cast with alloys that contain more tin and zinc. So there's a clear demarcation here between the older bronzes and the more recent bronzes around World War II and post-World War II. Again, we have a bunch of unclear data here, and we can say, for instance, that some of the data points belong to a cluster that is overwhelmingly pre-World War I, and therefore we can make a guess that it is probably also an older piece. Now, the last correlation we wanted to do was with the technique of casting. There's typically two main techniques, sand casting and log wax casting here on the right. And sand castings is typically done for larger pieces. You start with the main object as created by the artist. You then make sections of sand pieces that you assemble together into a mold that is now negative of the object. And then you cast the molten alloy and fill the pieces, and you end up with the casting. So we go from the object to a negative back to the casting. The lost wax casting is a little bit more complicated. You start with the main object. You then make a mold, typically made out of rubber, which is flexible, a single piece. You then fill that mold, which is a negative, with a positive made out of wax. You then take that wax positive, dip it into a fine ceramic slurry that becomes a shell. Remove the wax by melting, you end up with a second negative. And in that second negative, you now cast the object after this rather complex procedure. The main difference is that on the sand casting level, those are multiple pieces. You can see they're assembled together, so they're always seams, and the object must be then very carefully polished. It is, however, much more robust, typically, and well suited for high temperature casting. The shell for the lost wax casting tends to be very thin, and so there are issues with the shell breaking, for instance, during casting with complete loss of the object. And so it is usually used for smaller pieces, as well as pieces where intricate detail is quite important. So when we do this correlation, In red, we have sand and what we call lightly sand. This is now at the museum looking at the style of the object as well as the presence or absence of seams, deciding that it's probably a sand-cast object. Those are red or reddish, and you see that they cluster very nicely in clusters B and C, the higher melting point pieces. And in blue, we have lost wax that also cluster very nicely with cluster A for the lower melting brass objects. So here again, there's a clear demarcation between the two techniques, which again would help us, for the few unknowns that we have, help us tell us that yes, it is sand or lost wax casting. Here's an example, Matisse Lesser for sand casting, and here's an example for lost wax casting from Matisse again, woman waiting. So, to conclude, we plotted essentially the composition of zinc and tin, which are the main two alloying elements, against each other, and found that there were three main clusters, A, B, C. One is bronze, so it's very high in tin, and the other one are brass alloys. One is high, and the other one is lower in zinc. We found that those clusters, A, B, C, correlate very well with the artists. We saw that Picasso, for instance, was always in cluster A. The foundries, we saw, for instance, that Swati also tend to be together with cluster A. The casting dates, the most recent castings were in cluster A, and even the casting method. So there's clearly a correlation, in fact, between the foundry casting at a particular date with a particular method. Thank you very much.
Next and final speaker will be Dr. Kimberly Gray, who holds the positions of both Director of the newly established Institute of Sustainable Practices at Northwestern and Professor in the Departments of Civil and Environmental Engineering and Chemical and Biological Engineering at Northwestern. Does that make you 3 positions instead of 2? That's another professorship. Yeah. Her areas of expertise are environmental catalysis and physicochemical processes in natural and engineered environmental systems, with particular focus on energy and sustainability applications. Dr. Gray.
We're going to continue with discussing changes in color. Okay, let me just go back and see if this is working. Okay, good. So what I'm going to do is just talk to you a little bit about the historical context of this painting, because maybe, at least in contrast to what Kathy talked to you about, there's an awful lot known about this painting. And then if you'll sort of humor me, you get to, a civil engineer gets to talk to you a little bit about art history. See, I really wanted to be an art historian, but I wasn't very good. So it's much better at environmental chemistry. So, as we all know, Impressionism was that movement in France in the late 1800s where artists tried to capture light and capture light in quotidian scenes of everyday life and nature. And in Neo-Impressionism, what we have is sort of to take that a step further and to separate light into its component pieces, or to dissect light, and look at the individual colors making up the light. I mean, to the point where this is just pointillism. And the artists that are most known for that are Signac and Seurat, of course. And the masterpiece of Neo-Impressionism is Le Langevin. So this took about 5 years to paint, from 1884 to 1884 to 1889, and there were 3 phases here. In the beginning, Seurat used pretty complex pigments in making up his color. In his second phase, what he did is he used fewer pigments and sort of refined both his dots and his brush strokes and the figures. And then in the third phase, what he did is he added a border in order to enhance the luminosity of the painting. And I don't know how many of you realize this. I mean, I had to look at this a couple of times, but here's that border. I'm not sure how many of you were really aware of it. So what was really interesting about this painting was the fact that it began to deteriorate very, very rapidly. So if it's finished at about 1889, by 1892, Felix Fénéon, who's a very good friend of Seurat's, he's his big booster, his big supporter, but an art critic at the time. So here's Seurat, and here is Fénéon. What he is quoted as saying is because of the colors which Seurat used towards the end of this, 1885, 1886, so this is the second phase in which the painting is being painted, this painting of historical importance has lost its luminous charm. While the reds and the blues are preserved, the Veronese greens are now olive green, and the orange tones, which represent light, are now nothing but holes. So this is not a good thing for impressionists, right? For you to now have sort of lost that luminous charm of light. And what this is probably has come to be attributed to is the darkening of a zinc yellow pigment. Okay, so 100 years later, come forward 100 years later, the Art Institute is now doing a thorough evaluation of Le Grand Jaune, and my French mother-in-law, when she first visited the United States and we took her to the Art Institute, was quite upset that this painting was here and not in France, but could not understand why this painting was here. So anyway, the main pigments that were used were identified, and zinc yellow, it's a zinc potassium chromate, I'll show you its structure in just a moment, is the one that changed most significantly, and because this pigment was used in so many other mixtures, it had a very sweeping, extensive effect. And this change, this shift, as I noted, happened very, very quickly. So the question is, did the alteration associated with this loss of luminosity, this darkening of the yellow pigment, did it have something to do with redox changes in the chromium, which is one of, what makes up this paint, the zinc yellow? And what's shown here is, this is a photomicrograph, and it's taken at the top of the fisherwoman's hat, and what you can see, so this is the background of, I think this is the scent. And so what we see here is the darkening, how much the yellow, these dots were originally orange and yellow, and what we see is how much they darkened. Okay, so fast forward, not really fast forward, but move forward a few more years. It's now 2004, and the Art Institute has a project where they want to do an extensive re-examination for a 2004 exhibit on the making of Le Grand Jaune. And so they previously knew that the pigments that were in this painting were linseed oil, zinc yellow, starch, which is a major component, vermilion, which is a mercuric sulfide, lead white, soot, barium sulfate, which is a minor, and also vermilion is kind of a trace component as well. And so what's interesting is that despite the fact that this painting has been so well studied for so many years, there still was not an understanding of what caused the very rapid loss of luminosity. Why did the zinc yellow darken so quickly? Some other things that they, just to kind of give you more context here, that in this re-examination in 2004, this extensive re-examination, X-ray analyses were conducted and the drawings were discovered behind some of the figures. And also there was a digital rejuvenation that was conducted. Now, the point of our work was not to say, let's figure out a way to repair this and bring back the zinc yellow. I mean, that would be impossible. It's more just a curiosity question. Why did this darken so incredibly quickly? Now, lots and lots of variables can contribute to what we had thought, what we hypothesized to be a reduction of the chromium from chromate 6 to chromium 3. So some of those factors, environmental factors like humidity, light effects, was it a photochemical effect, did it have to do with acidity? And so with Francesca Casadillo, we engaged in a collaboration that went on for many years. So here is zinc potassium chromate. This gives you the chemical formula of that yellow pigment. This is how it starts out. It was first synthesized at the beginning of the 19th century, and it was thought to be, ironically, light fast. And so And Sorrow is the one who recommended it to Seurat. Now they've since realized it's not very light fast at all, and artists don't use it anymore, or use it at their own risk. I guess it has some other effects of corrosion inhibition. Just a little bit, being an environmental chemist, I just have to just say a few words about chromium here. So chromium-6 is rather toxic, in fact, very, very toxic. It has toxic effects to the respiratory tract and the skin. It's a potential carcinogen. It's highly soluble, mobile, and thus bioavailable, and it's tetrahedrally coordinated to oxygen here. So it has a very different chemical structure than does chromium-3, which is now has very little solubility, low mobility, low bioavailability. In fact, it is essential as a trace element. It's essential for life, and it has an octahedral coordination here. Okay, so what was our hypothesis? What sort of guided our inquiry? The color change of the zinc yellow pigment is due to the photochemical reduction of chromate, all right, from chromium-6 to chromium-3. And what we sought to do was to first create a chamber, an environmental chamber, that would allow us, under very controlled conditions, to accelerate this aging, and then to look at effects like humidity, acidity, and light and dark, having the effect of light. So we call these environmental aging chambers. And then, with this ability, we could now make samples under these different conditions and probe them or interrogate them with a variety of spectroscopic tools. Just visible spectroscopy, X-ray, photoelectron spectroscopy, infrared spectroscopy using an ATR crystal, and Zane's X-ray absorption spectroscopy. And then, if we're able to do this, now what we could do is to try to really identify or pinpoint if the changes are due to this reductive process as a function of what, and to elucidate the mechanism. So I'm just going to look at the time here, because I can just cut to the chase and tell you, this was really easy to do. This we could do, no problem. We could also make samples under controlled conditions to sort of tease apart different effects and interrogate them. But as to them being able to do this in a way, in a very complex organic and inorganic matrix is what makes our paint, and to determine exactly what sort of redox processing was going on, or what was the mechanism, this is something we couldn't do. All right. I mean, we certainly know more, but this was not something we could really do at the time. So I will. I think we have enough time. Okay. So what we could do then is to very simply create this environmental aging chamber in which we could control light effects, temperature, relative humidity. We could add a acidic gas, and we could vary that. We could look at SO2, we could look at CO2. And I've mentioned to you what the different components. I mean, we knew the different components in these paints, and we could make different kinds of paint outs and look at these interactive effects between these different components as a function of ambient relative humidity, a highly humid environment, acidity created with CO2 or SO2, and then light and dark effects. So as you can see, all right, so it would take about 3 months to make these paint outs because it took them a really long time to dry. And then the experiments, although they were, so in real life this happened over about 5 or 6 years. Well, let's see, is that right? It happened over, yeah, so it happened within 6 years. Well, sometimes we have a graduate student that lasts that long. We don't like that. Usually our postdocs are here at a much shorter time. So what we did is we accelerated this and tried to do the experiments in 1 month. Now, a chemist would say, how can a month experiment be quick? Okay, but environmental chemists were a little more patient. But still, what we're talking about are a set of experiments that, at most, and you're looking at all these different combinations. This, to get the light right here, this took about 3 years, to sort of look at all these different effects. All right, so what we could do is definitely induce light changes here. So what we see here are experiments that were done in 2005. Now, there's not very, so this would be the control, the beginning. This would be 1 year later, because what we thought we could do is we could just put these under a xenon light. We removed the UV component of the light spectrum, and we thought they would we would be able to observe the kinds of changes that were observed in, 1892. So this is 1 year. That did not happen. That was when we realized it was going to be something more difficult. So these are the kinds of changes that we were able to induce. So this control still functions for all of these. And you see that now what we're able to do is see the browning. And then here, under these, we were able to induce changes that have a kind of a green tone. Well, what happened to the zinc yellow is that it turned more brown, okay, not green. All right, so that's important to know for the moment. All right, so what people do when they're probing changes in color is that this is a very reliable visible spectroscopy. This is a standard technique. And what you do is you take the spectra and then you analyze that, the spectra along 3 different parameters that tend to mimic a human eye response to color and changes in color. So L gives us is an index of brightness, it's a black-white index. A gives us red-green hue, and the B gives us a blue-yellow hue. These also tend to be an index of the purity of color. Reflectance can tell us whether the color change is due to physical changes in the surface or to chemical changes. To give you an example of that, here is reflectance as a function of wavelength. So these were zinc yellow in the linseed oil that were aged for 1 month in ambient humidity and in an acid environment created by SO2. And what this shows you is that there was a chemical change because if this reflectance were completely flat, then you say it's a physical change. So the chemical change is going on, and there's a difference due to light. Whereas at much higher relative humidities, also in the presence of the same quantity of acid, there's no difference between light and dark, which tells us that the change in color can occur due to a photochemical effect or a non-photochemical effect. All right, so there's a couple of different things, there are a lot of things going on. All right, so anytime you're doing work that's, the color we see is a function of surface characteristics. But for many of these probes, what you do is you have a problem with how do you separate out the surface signature or what's going on at the surface from bulk characteristics. All right, so one way that we could use is ATR-IR spectroscopy is a way to just look at surface phenomena. The problem is that it is not sensitive enough. So in this organic matrix created here in I think linseed oil, I think we also add starch, we saw a change as a function of light, but what we couldn't do is to assign what that change was. What was that change due to? All right, so we could not find it in the literature, nor did we have a standard with which we could compare and assign, this sort of change we see, this spectroscopic signature is due to a change in the redox properties of chromium. That we couldn't do. But what we do know is that there are oxidative changes in the organic matrix, but they're not really associated with the kind of color change that we see. All right, so some partial conclusions are that at high humidity, that we modeled 90% humidity, there are non-photochemical changes in color that just the humidity alone induces. But they tend to create a green color. The degree or the extent of change is very similar to what was observed in Lagrange-Jacques, but the type of color was not the same. We were able to, at lower humidity, in the presence of acid, get the color change in quality that was comparable to Lagrange-Jacques, but we weren't able to induce the extent of changes, a quantitative extent. The color change was superficial. These other components tended to have very minor effects. And using XPS or ATR infrared spectroscopy, we really were not able to separate out surface from bulk phenomena. There were matrix effects, although we did see certain things like some incorporation of sulfur into the pigment. All right. So then we tried to use Zane's X-ray absorption spectroscopy. And with Zane's, what we can do is we can look at this near structure here and get a sense of the oxidation state. And here's chromium-6, has a very distinctive signature, very different from chromium-3. So we thought, if this change has occurred, this is a technique that should be able to give us that answer. All right? So we know we can induce different kinds of color changes to a different kind of extent, now could we assign that to a particular change in chemical speciation? Well, we run into this problem again of separating out what's at the surface from in the bulk. And the color change is just at the surface, all right? And now you can get around that by just sending in your X-ray beams and grazing the surface, except that these paint surfaces are not anatomically flat, all right? So in fact, there are little bumps on them, and so they act like the bulk. And so there was really we still get the signal averaging problem. I think I'll show you. Okay. All right, and we get another problem. Very large error bars, all right? And so what this shows you is we can try and make the sample as thin as possible to try and reduce the bulk effects. So these would be high humidity, the presence of acid. In general, the high humidity tended to dilute the acid effect. But you do see, and these would be the amount of chromate 6 that you saw in the thickness samples, and the sample thickness tended to increase this way. So if you ignored the error bars, you could see that there's sort of a trend here, okay, but they're just not statistically different. This shows you what happens with the a lower relative humidity. Once again, there's a difference in terms of averages, but the error bars are very large. So, to summarize then, what did we find? So we have this sort of matrix of what we thought were the major effects: humidity, relative humidity, acidity, and light and dark. And so, with low relative humidity, in the presence of light and acidity, as created with SO2, we found that we got a color effect, a color change, but to a lesser quantitative extent. But it was similar to the Lagrangian color, all right? Tended to turn brown. And the Zanes told us that maybe this could be associated with the chromate reduction to chromate 3 of 2 to 4%. Whereas, at the high humidity, this was not a light effect. Color changes tend to be green in color. They were similar, the extent of color was similar to Lagrangian, but the color wasn't, the quality of the color was different. Whereas the Zanes said that the chromate reduction was maybe about 10% here. All right. So pigment fading due to environmental factors, I think, illustrates the complexity of trying to tease apart any environmental phenomena, which happens in very messy systems. It's sort of the chemistry of soup. It's very difficult. And there's a huge limitation that's associated with the lack of direct methods because of the matrix effects you get, and just the time that it takes to do all the separate experiments to tease things apart. So on that note, let me acknowledge my collaborators. Jean-François Gaillard is a professor also in environmental engineering, and he's the one who did the XAFS work, the X-ray, or the XAFS work, with his graduate student, Luciana Zanella. Richard Lorca is a technician in our laboratory who built that environmental chamber and conducted all those experiments and took the visible spectroscopy measurements for so many months. Rahul Lee is one of my postdocs who did the XPS and the infrared spectroscopy. We collaborated with Francesca. Here are our collaborators at D&D CAT at Argonne. And of course, we were supported by, we started this work a really long time ago, and I can't even remember the year. Do you remember when this was? So this was even before we had the Mellon support. And Ira Uslander and NU Industrial Relations gave us some support for a year to kind of scope things out. And then we had Mellon support. So on that note, thank you very much for your attention, and I think I hand it back to Ruth.
I love when we cover such a wide range of materials. Thank you all so very, very much. I think we do have time, don't we, for a few questions? 5 or 10 minutes, 10, 15?
An hour.
An hour? Go for it, folks. Yes, sir.
I wanted to ask Professor Dunand, are the bronze of the antiquity, like a Marcus Aurelius that is still in very good condition, casted better than the brass of Picasso?
All right, so in fact, it's an interesting question because I've had the opportunity to work on bronze objects from China, about 3,000 years old. So I can't really comment on the Roman bronzes, which, by the way, were mostly copper tin, because zinc ores were not as available as tin ores. So all I know from the Roman time is that these were mostly copper tin, which tends to be, in fact, more corrosion resistant as a material than the brass materials, which contain zinc. Interesting enough, my personal experience, which is also on a project which belongs to that series of projects to get together with the Art Institute, was on those 3,000-year-old objects from beautiful Chinese vessels cast by, I believe, the lost was technique. But the main thing was that it also contained large quantities of tin, some quantities of silver and lead as well, and no zinc. So zinc, in a sense, the brass, is a relatively new alloy, at least for art objects, because it's well known, in fact, that copper tin bronze, while brittle, much more brittle than brass, is more corrosion resistant. So what you gain in terms of corrosion resistance with the bronze, you lose in some sense if you dropped one of those bronzes, for instance, in the shadow, whereas an alloy that is more zinc, more high in zinc, brass in other words, will not shatter, but will tend to corrode more heavily. Now, this is all dependent also on the patina and whether or not the object is exposed to outdoors. For outdoor objects, I would certainly go with bronze.
Any other questions? Yes, sir.
Yeah, Professor Gray, regarding the light reading, is there any effort to try to determine what the spectrum would actually be would see versus
So the only thing that we did in that context was to remove the UV light. So what we were trying to do here is accelerate the aging. And so we made sure there was no UV light, and the spectrum we created was a melanated light. So it was visible light. Certainly didn't have the intensity of outdoor light, but it didn't have the intensity of probably what was in Seurat's studio. But remember, what we wanted to do was to accelerate this. And we wanted to have measurable changes under controlled conditions and constant conditions. So they were illuminated constantly. So we didn't simulate a 24-hour cycle or anything. They were illuminated constantly for over a month. That's a good question.
What does the analysis you conducted of the deterioration in the Ron tell you what conservatives about conservation or about potentially bringing back some of the original colors?
I'm not sure it does. So I think that we fixed this problem by just never using this pigment. Okay. You know what? And that's how we fix a lot of the problems. Or you don't understand why, but what you do is to suspend the use. And I think it'd be interesting. I don't think you could restore this because these the paint are really complicated mixtures of the pigment. I think though what it does is it provides us with a more complete historical understanding, which is we have a more complete sense of the story. I also wonder if we were to restore it, would we change some of that history? I mean, it's, that's, I guess, kind of like a facelift, you know, maybe that's, maybe we shouldn't do it. I don't really know, but the interesting, I think what they did do is they went back and they did a kind of a computer simulation of what it would look like. And it's, you know, quite dramatic. So in this particular, but I could imagine in other cases, maybe where you had a less complex palette, that maybe this kind of understanding would allow you to change it. But in this case, you'd have to remove the zinc. You know, if you wanted to make something that was light fast, you'd have to remove this pigment. Or I don't know, you'd have to add some sort of oxidant to try to take it back to color. It'd be really complicated. I don't think you do it.
If I could just add to that, there are a number of examples, say when paintings are covered with a varnish. Those varnishes can be cleaned because you're not, well, probably Ruth should be talking about this as a museum person. Then you're removing dirt and discoloration of the varnish. But when it comes to trying to change or restore the painting itself, it becomes almost an ethical question.
And to add to that, the complexity too, if you're trying to, if you could do an environmental change, a reducing atmosphere or something that could possibly convert one thing, then what are you doing to the other pigments that are in the painting as well? You'd want to go back and check every single one of those to make sure that you didn't shift the painting into a red mode or into a blue mode. It's an extremely complex system.
Could you simulate the change? It's a digital era, right? So you can take the grand shot, do it digitally, and then can you do the changes that you suggested as used to be, and see how it looks like without actually restoring the thing, but then showing how it used to be.
That's been done.
I think there's a digitally enhanced image that was on display with Le Blanchard at the time. Is it still up? I'm not sure. Okay. Then it may be in a catalog that's available.
Is it any better?
It's different.
Actually, I have seen a digitally enhanced study of some of the ancient Greek buildings that were done, and they took them back to the way they used to look. They did it all digitally based on the scientific analysis. Anyhow, my question is, quite often there's a question, paintings, American or English. Iron, constant problem, American or English. Why can't we use isotopic ratios to, out of some of the studies you're doing, to identify metallic pigments or the source of some of the components of the iron or steel or metal objects, fireplace, instruments, whatever, to solve some of the problems of whether they're American or English? Because I can't imagine why that wouldn't be possible. We use isotopic ratios a lot to identify the source of things like lead. We can pretty much identify where lead comes from in the United States by the isotopic ratio. Why couldn't we do this with metallic pigments or with iron objects?
Here comes looking to. So we use isotopic ratios all the time.
Or other
for
tests.
climate. I just, I've seen them with respect to nitrogen, carbon, oxygen. I'm trying to think if I've ever seen one with respect to iron that's used. I mean, what would what geochemical process would fraction in iron? And I don't know, I've never seen that, but that's
I mean, there's certain tests we can do with wood to determine whether,
carbon. So anything that is biological, photosynthetic, plants will tend to enrich certain. So we have a you know, very rich information from nitrogen, carbon, sulfur, oxygen. But these are all minerals that are, iron cycle biologically. I don't know, you know?
The example you give about lead is the one I know for metals, because lead really comes from either uranium or thorium. And depending on the particular mine with different amount of uranium and thorium, the daughter lead has different isotopic ratio. I'm not really aware of other metals that would have
That's
this
my
kind of
only
different.
experience. That's why I asked if there were other tests or other.
But certainly for lead-based paints, which were used heavily, your suggestion is an example.
Yeah, but there's been a lot of work with that, because the tort lawyers wanted me to do that. I've done some work with lead. So we tend to look at the oxidation state of lead. So if we look at sediments, we can see right where, so sediments are you know, it's, you know, historic library of what's gone on in the past. We can see a layer of when fossil fuels, you know, contain lead. But it's not an isotopic ratio, it's looking at lead too. So you look at the oxidation state. I don't think it's as much isotopic. Is it isotopic? Yeah, because what they would like to do in with respect to lead-based lead poisoning, if it's due to exposure to paint, they'd like to be able to identify who the manufacturer of paint is.
I'm quite familiar with that.
Yeah, okay. And so that's been hard.
You could just alter the value of a lot of iron metal collections if we were able to do that.
There are a couple of questions in the middle. Well, you just said that.
In the study of bronzes, when you finished your correlation, did you go back to the trace elements and to see whether or not the trace elements showed up and gave you further clarification in the various A, B, and C?
Yeah, thank you for this question. Yeah, I didn't have time to mention this. We did this, so we looked at the potential correlation with lead, which was our third alloying element, in all the trace elements, and we found no correlation whatsoever. And frankly, there could have been correlation. We were half expecting some kind of correlation because, for instance, the supply of metals was time dependent. For instance, during one of the two world wars, there was a big shortage of the more expensive lead and tin. And so there was a lot of recycling, which may have shown in the form of higher level of those trace elements. So it's an excellent idea. The data essentially didn't show this, possibly because we had maybe only 70 or so objects. If you did correlations on hundreds of objects, we might see something. The other thing that I never mentioned is the relative cost of tin and zinc. Tin is a lot more expensive than zinc, and you add less typically, but still a bronze with tin tends to be more expensive than brass with zinc. And so we looked also at potential correlations with respect to the data, which it was cast, for instance, the Great Depression or World War II, and again found no correlation, indicating that if there was, a tendency for the foundry to use less expensive raw material, it was certainly not visible in our relatively small sample.
So I have a question for the panel regarding what artists do with the results of conservation work. Do they A, use that to alter their artwork so they last longer, or B, use knowledge of degradation processes to make their artworks dynamic?
I think B is the answer. And this topic came up in a seminar series we had about a year ago about house paints. And when Picasso started to use ripple-in house paints, the attractive part of that is that they dried so much faster than traditional artist paints. And the conversation went along the lines, well, we'd like to give more information to artists. And ultimately, the museum folks threw up their hands and said, well, that doesn't make any sense, because they'll go out and find the materials that they want to use for the life that they want to do.
I think the operative function is that information is provided to the art community, and it's the artist's decision whether they want to respond or use, or whether it changes their effects, because artists will go both ways. Some will actually invite the alteration and the degradation of the material as part of the living, the kineticism of their artwork, and others will be very, very particular about the archival quality of their material. And with that,
Well, I think you can see that we have a variety of really interesting and important topics. The issue of science and art is quite philosophical issue, so to speak, but with the rise, if you will, of modern analytical techniques, I think you can see the implications for art and science and part of the programs that we intend to develop. So again, I encourage you to join, and I also encourage you to fill out the cards and get some useful information about our design future program. I think we owe a vote of appreciation to our panel, and